you assign a unique binary codes to the states. So you've got a lot of ways of assigning binary states: minimum bit change, prioritized, adjacency, hot encoding, output paste, and so many of them. Okay, the cost and delay of a finite state machine is inherent in the input and output logic, and it depends on the assignment. Different assignments lead to different complexity in the next state and output logic. So an optimal assignment should give the simplest next state logic. In other words, the states that have the same successor, same next state, should have unit distant assignment. And those ones that have the same input output logic. So we will only look at two and mention the others. Okay, so the first one is called the minimum bit change. When you go through your machine, you should assign states such that when you go around, you will have a minimum number of bit changes. That is the first one. So here is your state diagram of your finite machine. What we are doing, what binary value will you give A? What binary value will you give D? What binary value will you give C and B? And does that impact on the behavior of the machine? So minimum bit change says, okay, assuming somebody says my A, I will give it 00, B 01, C 10, D 11. That is assignment. So let's look at the bit changes from 00. Your machine is moving like this, like a counter style. From 00 to 01, you've got one bit changing. 01 to 10, you've got two. 10 to 11, you've got one. 11, that is two. So in total, you've got 6 bit changes, 3 plus 3. First assignment. The second one is if they assign 00, 01, 11, 10. From here is 1, from here is 1, from there is 1, 1 is 4 bit changes. Which one is the best? The minimum bit change says this person's machine is more optimal. So you take the assignment that gives you the minimum bit changes when you move through the states. So this is optimal. That is what that one says. Let's look at that. Here is your machine. S0, S2, S1, S3, S4. Assuming you assign this, S0 is 00, S1 is 101, S2 is that, S3 is that, S4 is that. Another person says S0 is 00, S1 is 001, S2, S3, S4. And then we look at the bit changes. The machine from S0 goes to S1, S2, S1, S3, S1, S3, S2, S3, S3, S4, and then S4, S1. So those are the transitions. From S0 to S1, S0 moving to S1, from here to here, there are 2 bits that change here. From here to here is 1 bit. That is where we are getting those numbers. That will give you that. That will give you that. S4 to S1, S4 to S1. This one was 1 bit changes, another one, those are 2. S4 to S1, a change, no change, 2, 2, 2. If you add this, it will give you 7. If you add this, it will give you 13. Which one is the optimal assignment? It's this one that gives you 7. That is what the minimum bit change says. So this person will have designed his machine will be faster than that one. They could do the same thing, but one machine will be faster. So that is what the minimum bit change says. Now, let's look at this. You've got Q1, Q0, Q2. Let's put it in a K-map. If you're S0, we all said S0 is 00, maybe the initial state. With these assignments, S1 is there, S2, S4, S3. This one says S0 is there, S1, S3, S2, S4. From these, note that the next states are adjacent to each other. That is the conclusion. You've done this, leads to this. So you should note that. And we said B is better. So note the adjacents. This is the optimal one. States with a common successor are adjacent to each other in that map. So minimum bit change says you go through your machine, assign your state such that when it evolves, it will have a minimum of bit changes. Go through the transition. That assignment is the best. So that assignment is the best for this machine. Okay. Now we go to the next one. It's called the prioritized adjacency heuristic approach. Sometimes it's called the successor predecessor approach. Here is your machine, your state diagram. You have designed your machine, your state diagram. You've got state A, B, C, and D, and these are the transitions. What binary value do you assign A, B, D, and C? That is what you are looking at. So it says proceed by assigning adjacent encodings. Minimum bit change made us know that adjacent stuff should have something in common, which differ 1 bit only to all states that have a common destination or successor, source, or output. So here in the table, the K table, the first thing is the highest priority is given to states that move to the same state for a given input. States that move to the same state, states that have a common successor. Other books call it a child for the same input. Can you tell me which ones are those? Which ones will be next to each other? Highest priority in the K table. Which states have a common successor, have a common next state for a given input? Can you look at that and tell me which ones? I'm waiting for the answer. You can send me on the chat. Which ones, the highest priority, which one should be adjacent next to each other? Hello, I'm waiting for the answer. Yes? B and C. Sizwe, B and C. Jaswin, B and C. Let's look at B and C. Okay, simple. They've got the common successor, common next state. B, what is the next state is D when the input is 0. C, next state is D when the input 0. So B and C have got the same next state. You can call it a child. Different books use different words. You can call it a successor for 0. So that is why B and C should be next to each other. Highest priority. Second highest priority is given to the next states of the same state. States with a common predecessor, a common ancestor. That's why it's called successor predecessor. Which ones are those? Next priority. States which have got a common what? Ancestor. Remember here we are not talking of an input. You just, any two states that have got a common ancestor. The first one, you look at the input. The second one, just two states that have got a common predecessor, ancestor, or parent. Which ones are those? Okay, Sizwe, I've seen your answer. I'm waiting for other people. States with a common predecessor, ancestor, or parent. Some books call it parent. Which ones? I've received an ancestor. I've received an answer from Sizwe. I'm waiting for other answers. It's quiet. There is observing. Which states have a common ancestor, have a common predecessor, have a common previous state? Okay, I'm waiting for an answer, please. Forget about what you answered here. Just which ones? Okay, Lindelo, B and C again. Yes. Okay. B and C Mfundo. Yes. B and C again. First priority, B must be next to C. Second priority says B, whatever you do in the table, B must be next, must be adjacent to C. The third priority is given to the states that have the same output value for the same input value. Input, output. The same input, output. Which states are those? I'm waiting for an answer. When you are in a state, okay, Wendy, you say A and B. A 00, B 00. That is good. Linda, A and B. That's okay. So we move on. A and B have the same output 0 for the same input. Even state C and D. So those are those that we are just following rules. C and D. Yes. So now in that table, because this one can be represented by 2 bits. Assuming you put A here, can you fit in your states? Can you place your A, B, and C somewhere here? We are saying next, adjacent. First priority, B should be adjacent to C. Can you fit it, your states in that table and do your assignment? Draw that, assuming A is here. You have to fit in your states, the B, C, and D, and make sure that first priority, we said B should be adjacent to C. Whatever you do, second priority, B should be adjacent to C. And then last priority, A should be next to B, or C should be next to D. Can you place your A, B, C, and D there? Start with A as 00. Can you do your mapping there? I'm giving you 1 minute. When you are done, just send a chat and say done. Then we'll see your assignment. Send a chat when you are done. Should take you 1 minute. One, if you place A here, first priority says wherever you put B, it should be next to C. So if I put B here, C should be there. If you start with A as the initial state, that is one form. By doing this, you are saying A will be given 00, B will be given 01, C will be 11, D will be 10. That is not the only way. You can put B here and C there. Okay? But as long as B is next to C, and A is next to B adjacent, and C is next to D. That is what that says. If you have a question, you can ask. But we just want to reiterate the first priority, states with a common next state, successor, for the same input, II, are adjacent. The next one, priority is states with a common ancestor, predecessor. That's why it's called successor predecessor heuristics. And then the third priority is the states that have the same input output relationship. Here A and C must be next to together. So in today's aim is just to apply those rules. So if somebody on your own, I'm giving you, draw a table and the rules are here, and perform a state assignment for that. Can you take 3 minutes to do that, please? I will repeat that. This is your finite state machine. Can you do a state assignment of that diagram using the successor predecessor heuristics? When you've finished, just say done, and then we'll look at the answer. You have to assign priority of which states will be next to each other when you are designing the machine. Okay, so the higher priority states with a common successor, okay, for the same input. This S3 and S4 should be given highest priority. Medium priority states with a common predecessor or common ancestor. You'll find that S3 and S4 have got a common ancestor. And low priority states with input output, same input output relationship. You see S0, S1, S3, S0, S1, S3, S4. So with those in mind, you draw your map and do, assuming S0 is the initial state. This one says S3 should be next to S4. The second one says S3 should be next to S4. And then S0 should be next to S1 and S3. So if you put here S0, S1, and S3, S3 should be next to S4. That is the highest priority. So that assignment, or you can put it this way, that assignment, they are all options and they are all okay. So you can do that assignment and do that one. That is what we mean by successor predecessor heuristics. Can you now do that assignment for that machine? If you have a question, you just ask. You have to first of all list first priority, who will be next to who? Medium priority, who will be next to who? Lower priority, who should be next to you? Create a table, assign the initial state, and then fit in that table your states. So can you, first of all, list the priority? And you have to tell me first priority, second priority, and lowest priority. Can you do that assignment and finish it? Okay, I'm waiting for the first people who have done it. You have to do the priorities and then the assignments. I'm waiting for the first person, the first people who have completed. Yes. No, X. Attention, please. Somebody has asked, yes, when X here means is only one exit. So whether the input is 0 or 1, it will always go to D. Don't care. D will always go to A, whether the input is 0 or 1. Or if you want, you can have two arrows, one with 0, another one with 1. That is what X means. D will always go to A. The input can be 0 or 1, doesn't matter. First of all, you assign first priority, who will be next to who. So those ones who did that, those who have the same successor for the same input is what? B and C. They all go to D when the input is 1. X can be a 1 or a 0. Those ones who have a common predecessor, you B and C, and C and D. C and D, the predecessor is B. B and C, the predecessor is A. States with the same input-output relationship A, B, C. So the first priority B should be next to C. Second priority says B should be next to C and C should be next to D. So if you have A here, B should be next to C and C should be next to D. So you can do that assignment or do that. Is there anybody who has a question there? In answering this, I expect you to give me these priorities before you do the assignment. Okay. Now, this one, I'm giving you time, 5 minutes to do it on your own. Remember, the table should be, you do the assignments, the table should be Q1, Q0, Q2. I'm just showing you the table. So can you take your time? First of all, list the priorities, the way it is done here. High priority, medium, and low priority. And then just go to the end. 5 minutes. When you are done, let me know. Do the reasoning. Prioritize the states. High priority, medium, and low. And then put them in that table and do your assignment. When you are done, just send me a chat. The first thing is to assign high priority, medium, and low priority. Then you draw the table, you fix your initial state, which is A, and then you place the B, C, and D in the table. The rules are here. So if you've done it, you'll find that first priority A should be next to D, B should be next to D, A should be next to C, second priority, and third priority. So when you place them, if A is there, 0, 0, said it should be next to D and next to C. So you can have C here, D here, or vice versa. So that is the assignment you should get. Okay, I will just mention the others. One is called one-hot encoding. If you've got states A, B, C, why not just make one a 1 and the rest zeros? Why not do that? A is 0, 0, 1, B is 0, 1, 0, and C is 1, 0, 0. That is one, but you will make your system more expensive. It will be less faster. It will be slower. It is easy, but it's got its disadvantages. One-hot encoding. The next one is called output-based encoding. If you've got a system, these are your states, HG what? Next state. Why not? If you look at this combination, you find that HG, which is a next state, is unique for this combination. So you can code it in terms of the outputs. For example, HG, there is HG, it can be ST complement. I'm seeing a message here. Okay, I will deal with the most preferred method later, Sahil. So this one, you say HG is here, is unique here, and is unique here. So you can take it as a combination. This and these are the same. So it is ST complement, H1 complement, H2 complement, like that. And that is the coding. So these ones I'm just mentioning them. Another one, you can assign a binary value. You say A is 0, 0, B, just assign a normal binary value. Then you can even use gray code, then one-hot encoding. So there are so many ways of performing an assignment, but which one is the most optimal? Somebody has asked the question, which one is tested? The most optimal is the successor predecessor heuristic. That is the most optimal, the best, and that is what actually comes out in the exam. That is what is used. So you better know the successor, predecessor. The others are just for mentioning. Okay, so that is what this section is all about. That is what this section is all about. So just go back and look at the successor, predecessor heuristics and do the tutorial. And those are the things that we will apply some of these things when we go to the next chapter, which is asynchronous machines. Asynchronous machines are not used, but it doesn't mean in the future they will not be used. In fact, some of the latest texts don't have the asynchronous chapter, but we will still look at it next week. Don't miss it. They've got lots of problems that you need to know. So don't miss next week's lecture. So today the objective was just to do that part. Next week we'll deal with asynchronous machines. The following week, MSI components, and we should almost be done with the course. I'm reminding you that the due date for the first lab is Monday. The next lab is the following Monday, and then we'll have an assignment and another assessment. Is there any question? Okay, please don't miss the deadline for the lab. And if you have any question for the lab, I've put there the email of the demi that you should send a question to. Okay, so just consult him. Okay, if there is no question, then let's meet next week. Don't forget about the lab. You can start by playing